I guess I should record. I wouldn't worry too much about this lesson because we had it and they didn't. It's not going to be on the test. But I thought it was a decent extra kind of enriching thing to see the relationship between how what you have here that you're taking the integral of is the rate of change, and that is the derivative of the original. And if you get that conceptually, that's good enough. Now, Billy had asked me about this one, and I went through and talked about it a little bit on the in the video. So if this one has been keeping you awake at night and making you feel like you just can't move on without it. So if this is my original, this says the figure above shows the region which is bound by this graph of this. So this is a graph of my rate. So when I want to go back to find my original function, so this is the graph of my rate. This is my derivative. So just like we had talked about in the front, the integral of this that takes me back to my original function, this is my derivative. So when I come down here and I put b in for those x's, that change in x over time changes to a change in b over time because I'm substituting that upper boundary into it. And then they tell you that b is moving at this rate, so how is b changing with respect to time? They told us it was moving at pi over 2 units per second. So we have that value to plug in there. And just like all of our related rates program or problems, if I want to find the related rate at that moment, tell me what input-output value you're talking about at that time. I'm saying how fast is the area changing when b is equal to this. So once I get this value for b, I plug it into my rate function, which is here. So I plug it into my rate function, and 1 minus the cosine. So pi over 3, the cosine of that is going to be 1/2. So 1 minus 1/2 is 1/2. Divide by pi over 3 is the same as multiply by 3 over pi. And then change times by that rate. And that's how those pi's cancel out nice and sweetly. So that means that my area is changing at 3/4 square units per second as this b is growing. So, big ideas to pull from this problem. Number one, when I'm taking the area under the curve of this rate, that actually is my derivative. So this is the big thing that came from that unit, recognizing that story between your integrals and your derivatives being inverses. So if my original function is equal to the integral of my rate is equal to what's inside that function. If that's my upper bound, then that's what I plug in. And then I can, then from this moment on, it becomes a related rates problem. We go back to unit 5. So definitely an extension, definitely not surprised that it stumped many of you, but hopefully after explaining it, it's a little better, yes? Little? Okay. Great. So anybody not here that needs these notes? So 7-8 you all should have started with, and I'll put all the papers out here so you can come get whatever you're missing. And what this one talks about is us moving towards talking about things in there's two kinds of integrals we can talk about, definite and indefinite. If it's a definite integral, we know our upper and lower boundary, and we know what we're trying to take the area of the curve. We know more about our equation. If it's an indefinite integral, it's just going to be generically speaking, tell me what this equation might be, and I can use that someday when I have my boundaries. So we revisit that whole idea of inverses, and the operations that we know are inverses: addition, subtraction, multiplication, division, taking the square root of something and it's square. And remember I shared the story about that sweet thing who FOILed and factored all day long. So we could actually do that with the integral and the derivative. You could take the derivative of something and then take the integral and then take the derivative and then the integral, back and forth and back and forth. Just like we talked about tying and untying your shoes. So the interesting thing is when we're taking an indefinite integral, we lose the constant. Because here is where I'm finding the derivative. Well, that's okay. This 2 comes out here and x to the 1 less power. So multiply by the exponent. Subtract 1 from the exponent. The variable stands. And then, of course, if this is x to the 0, I don't have any x's, so that ends up being a plus 0, right? The derivative of a constant is 0. So what we talked about was, okay, so which original function has a derivative of 2x? All of them. So how do you tell the difference between them? And that's where we talk about this plus c. And how hilarious that when I was doing this video, I was so excited I ended up forgetting all my plus c's. But
Yeah.
did you laugh at that? I'm like, oh snap, I got to go back. So we call it an antiderivative. So taking the integral, we can remind ourselves, hey, that was when we added up all of the little rectangles, and those rectangles were your height times your width. That change in x needs to be there because it's a limit as your change of x approaches 0. And then remember, this is like the height of the rectangle, this is the width between b and a. We simplify this by just using this symbol, taking the integral, and that's what takes us from our rate to our original function. When we take the derivative, we're looking the change with respect to x. So usually it's dy dx, or it can be dt dx, whatever variable we're working with. And if we call our original function our capital F, when we look at our rate function, whether we use the prime notation or the lowercase f, we need to understand that. Okay, so when we looked at the difference between the power rule and the inverse, we end up looking at the steps that we take. We multiply by the exponent, we subtract 1 from the exponent. So x cubed becomes 3x squared. Okay, well if I have 3x squared, when I go to take the integral of it, to take it back to my original function, I'm going to undo these steps. So instead of subtracting 1 from the exponent, I'm going to add 1 to the exponent. Instead of multiplying by that exponent, I'm going to divide by the exponent. And the kicker here is I want to make sure that you know that you're going to divide by the new exponent. So maybe that messed a couple of you up. So when I go to take the integral, and this 3 comes along with it, and you'll notice that's how I get myself back to my original value. And I can check it by then taking the derivative of it. So you end up doing that, think backwards, and it's one of those things, the more you do it, the more used to it you get. Questions on the front of this sheet? Okay. In the back here, just a bunch of the same thing. This 3 comes along for the ride. I write my x. I add 1 to the exponent, divide by the new. And then whatever simplifying I can do, making sure I add my c on to the end. Should probably add my c up here too. And again, when we talk about the difference between a definite and an indefinite integral, with your trip project, that was a definite integral because you had your distance from A to B. And this is where we were definitely knowing what area existed under the curve. Now what we're doing is we're just coming up with a general rule. We're just coming up with a function that could be applied to anywhere on the curve once we're given the A and the B limits. Or boundaries, upper and lower limits. And then we end up having to kind of look for ways that we can get back to what we know how to do. Like, we don't know how to do this yet. So if I distribute my x, now I get myself back to something I can do. So your homework was filled with ones like that. Of course, E is everyone's favorite, and we keep asking ourselves, okay, well, what function gives me this derivative? That one. What function gives me this derivative? And this was a tricky one to think about, because when you look back at our derivative chart, the derivative of a to the x is equal to a to the x ln of a. So how do I get just a to the x as my rate? I must have had an ln of a that canceled out somewhere, and that's what I give myself back. So this is one that we can logic and understand conceptually, but then it ends up being one that we're just going to memorize. And I put memorize in quotes like this because our plan was to give you these on the test. So we're at the point now where we want to make sure you understand the idea of calculus and what you're supposed to be doing, but you're not taking an AP test on it. So having that in the front of your brain is not necessary. Save the space for what you need for your other tests, kind of things. So logs, what kind of function gives me this as a rate? When you look back, oh, that's my ln. So you get this kind of conversation. If you were curious about this one, we were able to rewrite it like this and then do some fun math. And maybe you were curious, well, why can't we just rewrite this one as x to the -1, but notice if I add 1 to the exponent and then divide by the new exponent, I'm dividing by 0. And that's something that is undefined. I can't do that. So if I am taking the integral of 1 over x, that's going to give me the L out of x. And that's the opposite of those derivative rules. So you can look at each of those derivative rules we have on the back poster and kind of now work backwards. And that's what the next lesson is all about with the trig. So if this is my rate and I want you to integrate it, I'm asking you to come back and tell me what is the formula for the area under that curve. This is it. So you're coming up with a general formula by undoing all those derivative rules. Got it? All right. So then, as part of your video notes, I asked you to do this, and this is that second page that's there. Anybody want to ask me a question? Because I believe I went over and talked about this on the video. Yeah? So you either did it on your own and checked your answers with me, or we did it together with you definitely thinking and doing all of your own work. Right? Anybody want to talk about any of them? So I started coming up with these silly symbols where you have to look for ways to simplify. And then this is just going to be that one that you memorize. So extra copies of this worksheet are back there, pile number 2. Anybody want to talk about it? Anybody want to have a question? Front, back? Go. The first one? Okay. So with this one, I'm going to take my x, I'm going to add 1 to the exponent. And then I'm going to divide by that new exponent. I don't know. Because I had this sign here. I don't think it's a negative. Do you think my pen hit it by accident?
They dash in when you write the red notes afterwards.
Was that what it was, maybe? Yeah. It's definitely not negative. Say it again? Okay. Anything on the back? 11. When I looked at 11, I rewrote this as x to the negative first times x to the negative 1/2. Does that make sense to you? Who asked about this one? I heard it. Okay, Nadia. So do you see how I rewrote this as x to the negative first times x to the negative 1/2? Okay, so in exponents, if I have the same base, I can add the exponents. So I can rewrite this value as negative 2 over 2. So when I add these two together, that's how I get negative 3/2. Now that I have this in a way that I can manipulate, I can definitely integrate it. So here's my x, and I'm going to take it to the 1 more power. So that's over here I have negative 3/2 plus 1, but my 1 is in the form of 2 over 2. So that's how I get negative 1/2 as its exponent. I divide by that new exponent. So dividing by 1/2 is the same as multiplying by 2. That negative sign, well, my whole value is negative. And then x to the negative 1/2 power means I'm taking the square root, and it's down in the denominator. If you left it like this, it would still be right. It's just not simplified. Do I see another question?
For number 8, why put an x next to pi?
Number 8. Because that pi is a constant. So I want you to imagine if it was like a 2 or a 3, right? So if I was finding the integral of x plus 2, I would take each term and I would write it to the 1 more power, divide by that exponent. Here I have x to the 0. So to the 1 more power is x to the 1, divide by 1, right? So this 2 represents a constant, and that's what ends up happening here. This pi is a constant value. Uh-huh. Because if I were to take the derivative of this, it would be 1 times pi, x to the 1 less power, right? Then it would just be pi. You good? Anything else on this homework? What do you want to talk about? So I loved this bottom part. Predict what do you think the following antiderivatives are. And again, that whole chart is our next lesson. Because all you got to do is instead of reading it from left to right, you read it from right to left. If you want to know cosine, find what function has a derivative that's equal to cosine. That integral is going to be sine. If you say what has a derivative that's the opposite of sine, that's going to be, and notice this is the one that's negative now. So in your head, you should be asking yourself, like, how did I get that rate? What original function had this derivative? And that poster back there has them all. But that sign in the back talks about all of these trig antiderivatives. And all you need to do is have these written down in a place where you can reference them. Because if you need to take the integral of cosine, that's going to be sine. If you need to take the integral of sine, that's going to be the opposite of cosine. Because remember, cosine is the opposite of sine, right? When you take the derivative. So every single one of these, and in fact, when Ms. Holdaway and I filled out this chart, we were looking at that. We went backwards. Oh, cosine is sine. Sine is the opposite of cosine. Secant squared tangent. Secant tangent secant. Like we went backwards. That's the poster that we used when we were filling this out. So then the only thing here you need to think about is, okay, what do I need to manipulate to get things back to what I recognize? Because these are the ones that you know how to do. And we put that together. Now, what we have down here, this is my favorite part of finding an integral. Because it reminds me of when you're writing an equation of a line and you're solving y equals mx plus b, you have to plug in for b. Remember that back in Algebra 1? So here, if this is the rate and I'm looking for my function, what I'm going to do is take the integral of that rate. And this kind of goes to that lesson that they skipped that we did. If this is the rate, then go ahead and integrate the rate to get yourself back up to the original function. So when I go ahead and I do this, now I've got my original function, f of x, and I know one ordered pair. I know that when pi goes in, pi minus 2 comes out. Here's my input, there's my output, here's my x, here's my y. So when I integrate this, I get this phrase. Now f of pi is going to be equal to, I put pi in for my x's right here and here. I put pi minus 2 in for my output, and that allows me to solve for c. And once I solve for c, now I know where that function is. So on everything, this is the best part, to be able to go ahead and somebody gives you one solution that works, you're like, oh snap, I can plug that in and figure out what it is I'm missing. That's the cool part of this one. On the back, we have your reciprocal of your trig identities and your quotient identities. And then from here on out, it's literally just a matter of trying to see what you can manipulate to what you recognize. I don't know what to do with sine when it's in the denominator, but I do know what to do with cosecant squared. This one, I spent a long time looking at those things. I'm like, okay, cosine squared secant, I don't see it, I don't see it, I don't see cosine squared secant. And then I realized, oh, secant is 1 over cosine, so one of these cosines cancels out. So I do know how to integrate the cosine of x. That's going to be equal to sine of x plus c. If they gave me an ordered pair that was a solution, then I could solve for c. I rewrote cosecant x as sine, and then that's what I know how to do. All right. Here's my key that I made after the staples were inserted in my head. And I was a little cross-eyed. So let's see how many mistakes of mine you can find. I did a plus C on every one.
Sure.
No, I'm checking now. All right. So again, we're going to use the same conversations, and if the symbols help you, you know, your first thing is to go ahead and look for things that you can change. And I can distribute that, but because that's x to the 1/2 power, when I'm multiplying exponents with the same base, I add the exponents. So that's 1/2 plus 4/2, 1/2 plus 2 over 2. So that's where that 5/2, 3/2, and 1/2 come from. And notice I haven't integrated yet, so I still need my symbol and I still need my dx. Now when I go to integrate, I add 2 over 2 to each exponent, and I divide by the new exponent. We'll divide by 7/2, the same as multiply by 2 7s. How are we doing on number 1? Do we agree? Ricardo gives me thumbs up, I love it. Hey, theta is the same as x. So in a trig conversation, x and theta are your variable for your angle measure. In trig, it's an angle measure. So you treat theta the same as you would x. You raise the exponent by 1 and then divide by the new. This one, I'm like, oh snap, I don't know how to do that. So whoop, I go back and I'm looking at What function has a derivative of secant squared? Oh, that's just tangent. Plus c. Anthony, did you get them both right?
Yeah, I'm actually doing pretty good right now.
There you go, I love it. All right, the integral of 1 is x, because the derivative of x is 1. Do you see it? Back and forth, back and forth, back and forth. Cosecant x, cotangent x. I'm looking on my sign. Cosecant, cotangent, that looks like cosecant. Don't forget your plus c. And don't forget there's some negatives involved there, so this minus becomes a positive. 7x plus c for number 4. Those are the easy ones. We want to make sure you get them right, right? Guaranteed to get some of those. Okay, so raise your exponent by 1, divide by the new. Cosecant squared. I'm looking. Oh, that's cotangent. I get you. And there's some negatives involved. Now for this one, I don't know how to do this one yet, so I'm going to simplify it. So x squared plus 2 squared is x squared plus 2 times x squared plus 2. So my first terms, my outer and inner, and my last terms. And once I simplify this, and this is again one of the ones that I look to simplify. And by this point in the worksheet, I'm pretty good with this. I'm pretty good with that add 1, divide by the new. When I first started doing it, I'm like, oh, which exponent do I divide by? And what do we mean by add 1? And what do I do with that coefficient? Now, I got it. That's why we practice. When we practice math, we learn math. Anybody get to the back? Ricardo did? Are you getting them all right so far?
Yeah.
I love it. All right, so 5 goes to 5x. Secant squared, I look back at my chart. Yep, that's tangent plus c. I rewrite the square root of x as x to the 1/2. And I've done enough of these fraction ones now that I just know that's that multiplying by the reciprocal thing. I got that down. Here's the one that is completely memorized. Just memorize this guy. Either that or memorize where it is in your notes.
For number 9, wouldn't the antiderivative of cosecant be cosine and not cos?
So that is not your fault because Miss Holdaway came and told me today she meant to have a squared there that she forgot.
Oh.
So with the squared there, cosecant squared gives you cotangent. Yeah, but without it, we don't have a rule for cosecant. So that wasn't one that you would have been able to do. Because we could have put cosecant as 1 over sine, but we don't know how to do sine in the denominator. So that would have left you stuck. So you get a Smarty for picking up on that. Does that finish the chart? Or did we finish the chart before?
No? I mean, I'm so confused. That's the last Smarties that I've had.
I'm looking to see if Kayla's lying to me.
What? I'm just trying to see it.
I love it. All right, I'll get it to you while you're working on your next task.
What? Next test?
Task.
Oh.
So these are the two that I love the most. And again, here was another mistake. This is here. Like this doesn't help you, but you need to know that a sub 1, an input of 1 gives you output of 4, and then that's what this math is here. So it's okay if you didn't get that. But it's on the video, and if you want to try it and come back and check your answer, then you can. Make sense?
Would that be on?
Yeah. Yeah, because this is really what it's all about. we can integrate and get from the derivative back up to the original function, but we're stuck with that plus c until somebody says, oh, here's a solution to your original function. And being able to take that solution and solve for c is that final step. That's like the bow on the package. This was a problem because it should have been h of 1 is equal to negative 4. Without knowing this, you couldn't have solved this one. Okay? So we need to make sure that you know that this doesn't help you. This is what you need. Okay? Like down here, you can integrate this, Billy. You can integrate this. If this is my rate, you can take it back up to your original function. But you're stuck with this plus c until somebody gives you an xy ordered pair that you know makes it true. But once they do that, then you can plug in and get your original function.
I don't remember 12. Isn't it supposed to be 2x over 2, not 3x cubed?
Hold on. I think you're right. So this should go to 2x squared over 2. And it doesn't make a difference here, luckily, because my input value was 0. So the rest of everything is right.
Would your answer be y equals x squared minus cosine x plus 5?
Absolutely. And it should be no fraction here.
And it'd be plus 5 or plus 3.
Why would it be plus 5?
Because your z equals 5. Oh, no, I plugged it.
I think I'm okay with the 3.
Wait, where'd you get your 3?
Because when I plug in 0 for my input, this whole value is 0. See this whole value here?
Right.
That's 0. And I plug in 0, so the cosine is 0 is 1.
Yes, then you add 1, and that'd be 5. Right? Because you have,
Oh, I dropped my negative.
yeah, so that'd be minus 1, so you add 1, so that'd be 5.
That's awesome.
That's like 5
It's totally. Are we good? We like that better?
Yeah.
Nice. Okay, so here's what's next. All right, so here is the sheet. I'll make it nice and big. So here is the sheet. It's this indefinite integrals shuffle. So instead of doing it online, I like paper better. So you're cutting out each of these integral squares. 1, 2, 3, 4, 5, 6, 7, all the way up to 16. And you're placing each integral so that it's matched up with its original function. So the integral is going to match up with its original function. So the way that it's placed here in these boxes, not the right order. And our hint to get you started is box number 10 goes here. So, for example, if you go to take the derivative of this, you know that you'll end up with 3x squared minus 2x plus 5, which means that you'll be finding the integral of this, so you need to find the guy that has the integral of this rate. So whether you think of it as finding the derivative of your expressions or the integral, you want to find a way to match all the boxes into the shapes. Got it? And Marcus, I go.